In more advanced math courses, it is often necessary to be able to read a problem, draw a diagram based on what you have read, and then determine some mathematical relationship from the diagram. In this videotape, we're going to practice doing this. Before we start the videotape, you should obtain a copy of the problems that are going to be worked out on this tape from the supervisor of the math lab. Okay, if you don't have a copy of the problems right now, stop the machine and get a copy before we start. Okay, the first problem that you have on your sheets is the following. A man 6 feet tall is standing X feet from a street light. If the light is 10 feet above the ground, express the length of the man's shadow in terms of X. Okay, we have a situation like this. Here is the ground, here is the street light shining out on us. And the light is 10 feet above the ground. And we have a man standing X feet from the street light, and he's 6 feet tall. Okay, let's say here's our man. He looks a lot like the street light. Okay, except the man is wearing a hat. And he is 6 feet tall. He is standing X feet from a street light. So the distance from the man to the street light is X feet. Okay, now as he's standing here, the light falling on the man produces a shadow like so. Let's call the length of the shadow S. Now what we're trying to do here is to express the length of the man's shadow in terms of X, or as a function of X. Okay, we started off, we read the problem, we've drawn a diagram based on what we've read, and now we're going to try to determine the length of the man's shadow. Express that as a function of X or in terms of X. We would like an equation linking S and X. Okay, now what we have here is a situation like so. We really have two right triangles, a larger one and a smaller one. This is the man, 6 feet tall, the street light, 10 feet above the ground. X represents the distance between the man and the street light, and S the length of his shadow. Okay, we're looking for an equation linking X and S. We would like to have an expression for S in terms of X. Okay, we notice that these two right triangles are similar to each other. We have right triangles. The right angles are the same. The larger right triangle and the smaller right triangle, they share this angle here, so of course the third angles must be also the same. These two triangles are similar, and we do know that corresponding sides of similar triangles are in proportion. We can set up a ratio. We can say in the smaller right triangle, say that the length of the base of the smaller right triangle, S, is to the height in the smaller right triangle as the length of the base in the larger right triangle, which is S plus X, is to the height of the larger right triangle, which is 10. Let's look at that again. Okay, the proportion is based on the two right triangles, which are similar to each other. We work in the smaller right triangle, and we say the base is to the height in the smaller right triangle, that is, S is to X, as the base is to the height in the larger right triangle, S plus X is to 10. And we're trying to express the length of the man's shadow, S, in terms of X. So we'd like to solve this equation for S in terms of X. Okay, the first thing we might do to get rid of the fractions is to multiply both sides by 30. Lowest common denominator. Okay, we multiply both sides by 30, which is a legitimate thing to do. We can multiply both sides of an equation by whatever quantity we would like. And when we do this, the 6 goes into the 30 here, leaving us with 5s. Here, the 10 into the 33. So we have 5s is equal to 3 times s plus x, or 5s is equal to 3s plus 3x. We'd like to solve for s in terms of x, so let's get s on one side. We subtract 3s from both sides of the equation, giving us 2s is equal to 3x, and then dividing both sides by 2, s is equal to 3 halves x. We now have expressed the length of the man's shadow, s, in terms of x, or as a function of x, where x was the distance between the man and the street light. For example, if we knew that the man was 5 feet from the street light, if x was 5 feet, we could substitute in here, x is equal to 5, and we would get that s is 3 times 5 over 2, 15 halves, or s would be 7.5 feet. So if the man in this problem is standing 5 feet from the street light, the length of his shadow is 7.5 feet. And in a similar manner, if since we've expressed s as a function of x, if we know what x is, we can very easily solve for s. The second problem on our sheet is the following. A rectangular piece of paper, 8 inches by 12 inches, is to be used to make an open box by cutting out congruent squares from the 4 corners and folding up the sides. If the squares are each x inches on a side, what is the volume of the box in terms of x? Okay, we are starting with a piece of paper, 8 inches by 12 inches. And what we're planning to do is to cut out congruent squares, squares of the same size, from the 4 corners, and then to fold on the dotted line to produce an open box, which would look something like this. And what we'd like to express the volume of the box in terms of x. Remember, x represents the side of a square that we are cutting out. So this square here is x by x by x by x here, and similarly, each square has side x. We're cutting these out from the 4 corners. And we'd like to write down the volume of this box. Well, we know the volume of a box is going to be the length times the width times the height. But we'd like to write this all in terms of x. Okay, to help you understand, I have taken a piece of paper, okay, from which, say, 8 inches by 12 inches, and I've cut out corners, the 4 corners here, cut out squares from each of the 4 corners. Okay, and what we're going to do now is fold on these lines here, and we're going to form a box. Okay, this is what we have over here. And we're trying to find the volume of the box. The volume, of course, is the length times the width times the height. All right. We'd like to express the length, the width, and the height all in terms of x. Okay, now, you notice that when we cut out the corners here and here, this was originally 12 inches. We cut out x here, and we fold up. Okay, we get the length of the box is now 12 minus 2x. 12 minus 2x, it was originally 12 inches from here to here. We took off x on this end and x on that end, leaving us with 12 inches. That's the whole length. Take off x here, take off x there, just 12 minus 2x. This is the 12 minus 2x. And when you fold it up, that becomes the length of the box. Similarly, we have 8 inches here. We've taken off x here and x here. And we're left with 8 minus 2x for the width of the box. Now the height. We have this, and we've taken off a square, x by x. Now when we fold up to get the height of the box, the edge of the square becomes the height of the box, so that the height is just x. Okay, we had 12 inches, we took off x and x, so we have just 12 minus 2x. For the width, we had 8 inches, taking off x and x, 8 minus 2x. Now when you fold up, the edge of the square becomes the height of the box, and we have just x for the height. So we can write here now that the volume, which is length times width times height, is 12 minus 2x times 8 minus 2x times x. And we've expressed the volume of the box in terms of x. In our third problem, we have the following. A 60-inch piece of wire is to be cut in two parts. One part is to be used to make a circle, and the other part is to be bent into a square. If x represents the amount of wire to be used to form the circle, express the total area enclosed by the two figures as a function of x. We have a 60-inch piece of wire. One part is to be used to make a circle and the other part to be bent into a square. Okay? Here's our wire. It's 60 inches long. We're going to cut it at some point. Let's say here. This part will be x inches long, and this part here, what's left over, of course, would be 60 minus x. X and 60 minus x, because it has to add up to 60. Now, x represents the amount of wire used to form the circle. So this x here, we're going to take and use this to form a circle. So x will be the circumference of the circle. Then the 60 minus x is going to be used, this remainder, the wire here, is going to be used to form a square. Okay, the rest of the wire is used to form the square. So we could do it this way. The perimeter of the circle, also known as the circumference of the circle, is going to be x. the perimeter of the square, okay, will be 60 minus x. We have x inches to bend to form the circle, and 60 minus x inches to bend to form the square. The perimeter, the distance around the circle is x, around the square, 60 minus x. Okay, let's say the circle has radius r, and that the length of the edge of the square is s. In other words, this is s, 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 s. The total area enclosed will be the area of the circle plus the area of the square. The area of a circle of radius r is pi r squared. The area of a square of side s is s squared. The total area, as I said, the total area is the area of the circle plus the area of the square. The area of a circle with radius r is pi r squared. The area of the square, whose edge has length s, is s times s, or s squared. Okay, so we have the area in terms of r and s. However, we were asked to express the total area as a function of x. We have to get it in terms of x. And the way we're going to do that is to figure out what r is in terms of x and what s is in terms of x. Well, the perimeter of the circle, or the circumference of a circle of radius r, is 2 pi r. And the perimeter of a square, if the length of an edge is s, would be s plus s plus s plus s, or 4s. And we can use this to figure out what s is in terms of x and what r is in terms of x. Let me rewrite those two equations up here. We have that the perimeter of the circle, which was made out of x inches of wire, is 2 pi r, the circumference of the circle. The perimeter of the square, which was made out of the remainder, 60 minus x inches of wire, it's of course 4s. All right, so taking this, we can solve for r. R, dividing both sides by 2 pi, r must be x over 2 pi. Divide both sides by 2 pi, x over 2 pi is equal to r. Similarly over here, dividing both sides by s, s is equal to 60 minus x. Dividing both sides by 4, s is equal to 60 minus x over 4. Okay, so we took the top equation, x is equal to 2 pi r. We solved for r by dividing both sides by 2 pi. R is equal to x over 2 pi. Similarly here, we solved for s. We divided both sides by 4. S is equal to 60 minus x over 4. Okay, now we're ready to substitute in here. The total area is pi r squared plus s squared. But we now know that r is x over 2 pi, and that s is 60 minus x over 4. Okay, so we have the total area expressed as a function of x. Okay, the last problem on the videotape is the following. Problem 4. An athletic field is in the shape of a rectangular region with a semicircular area on each end. if the radius of each semicircle is R, and the total perimeter of the field is 1,000 yards. Express the area of the field in terms of R, or as a function of R. Okay, we have a field, rectangular region, and a semicircular area on each end. The perimeter of the field is 1,000 yards. That's the distance around. You can imagine that there's a racetrack, say, around the playing field, and the perimeter is to be 1,000 yards. The radius of each semicircle is R. The semicircle is, of course, congruent. Okay, and we're interested in expressing the area of the field in terms of R. Let's let X represent the length of the rectangular region. Then this would also be X. The opposite sides of the rectangle are going to be equal. The total area would be the area of the semicircle on this end, plus the area of the semicircle on that end, plus the area of the rectangular region. The semicircle here and the semicircle here together give us a circle. So we have this, really we have, if these two circles were to put together, these semicircles would be put together, we would have just a complete circle of radius R. The area of a circle of radius R, of course, is pi R squared. The area of the rectangular portion, the area of a rectangle, is length times width would be X times 2R, or 2R times X. 2R being the width here, X being the length. So we have the area is pi R squared plus 2RX. However, we would like to get the area of the field in terms of R alone. Okay, the pi R squared business is okay. The 2R is okay. Here is what we have to get rid of. We would like to get X in terms of R. Well, we were given some extra information in this problem. We were told that the perimeter, the total perimeter, is 1,000 yards. That's the distance around the entire field. The perimeter is 1,000 yards. Now, we have the two sides of the rectangular region. That's X plus X. Plus we have the perimeter, we have the length of the semicircle here and on that. Well, the two semicircles together would give us a complete circle. If we take this distance and this distance, together it gives us the circumference of the circle. The circumference of the circle of radius R is 2 pi R. That's the distance around. So we have actually pi R over here, pi R over there, together 2 pi R. So we have that 1,000 equals 2x plus 2 pi r. And we will be able to solve that equation for x in terms of r. The total perimeter, okay, x plus the two semicircles together giving us a whole circle, the circumference of which, the perimeter of which is 2 pi r. Okay, so we have 1,000 is 2x plus 2 pi r. From this we can see that 1,000 minus 2 pi r is equal to 2x. We're dividing both sides by 2. X is equal to 1,000 minus 2 pi r over 2. And we can simplify a little bit. We can factor out a 2 on the top, leaving us with 500 minus pi r. And we have a 2 on the bottom. See, on the top we have 1,000 minus 2 pi r. We have factored out a 2. We can now divide top and bottom by 2. So we get that x is equal to 500 minus pi r. Now we can take that value for x and substitute it back over here to get that the total area is pi r squared plus 2r times x, but x is 500 minus pi r. So now we have the area completely in terms of r. And that brings us to the end of this tape.